Start with two medial lines, commensurable in square only, A and B, such that their product, AB, is medial. We'll show that A plus B is irrational. Let DG equal A plus B squared, equaling A squared plus 2AB plus B squared, and let DH equal A squared plus B squared. So, DG minus DH is equal to 2AB. A and B are medial, so A squared and B squared are medial, and AB is medial, so 2AB is medial. So, DH and DG minus DH are medial, which, by proposition 10.22, means H and G minus H are both rational and incommensurable with D. Now, A to B is proportional to A squared to AB, and A and B are incommensurable, so A squared and AB are incommensurable. A squared and B squared are commensurable, so A squared plus B squared and A squared are commensurable. 2AB and AB are clearly commensurable, so A squared plus B squared and 2AB are incommensurable. Or, DH and DG minus DH are incommensurable, so that H and G minus H are incommensurable. H and G minus H are rational, but commensurable in square only, so H plus G minus H, equaling G, is binomial and thus irrational. An irrational times a rational is irrational, so DG equaling A plus B squared is irrational, so that A plus B is irrational. To recap, A and B are medial lines commensurable in square only, such that their product is medial and their sum is irrational. We'll call this type of irrational number a second bimedial. An example of a second bimedial is the fourth root of 20 plus the fourth root of 45. To show this, let A equal the fourth root of 20 and B the fourth root of 45. A equals the fourth root of 20, which is equal to the square root of 2 times the square root of 5, the geometric mean of 2 and 5, which are rational by Euclid's definition, but commensurable in square only, so the fourth root of 20 is medial. B equaling the fourth root of 45 is equal to the square root of 3 times the square root of 5, the geometric mean of 3 and 5, which are rational by Euclid's definition, but commensurable in square only, so the fourth root of 45 is medial. A and B are not commensurable, but their squares are, because A squared equaling the square root of 20 is equal to 2 root 5, and B squared equaling the root 45 is equal to the 3 times the square root of 5, and they're both measured by the square root of 5. Finally, AB equals the fourth root of 20 times the fourth root of 45, which is equal to the fourth root of 20 times 45, which is equal to the fourth root of 900, which is equal to the square root of 30. To be a medial area, the square root must be medial, and the square root of 30 is equal to the square root of 6 times the square root of 5, which is the geometric mean of the square root of 6 and the square root of 5, which are rational numbers by Euclid's definition, and they're commensurable in square only, so the square root of 30, being the fourth root of 30, is medial, and the square root of 30 is thus a medial area. So in conclusion, the fourth root of 20 and the fourth root of 45 are medial lines commensurable in square only, whose product is medial. So the fourth root of 20 plus the fourth root of 45 is a second bimedial. When looking for such a number, a good rule of thumb is one of the form the square root of A root B plus the square root of C root B. But be sure to check all the other conditions.